Starting my recording late, but it's all in the handout. So what is it doing? Well, it went through the Vero Log codes. That's pretty simple Vero Log code. But now it's looking at timing analysis, and it's looking at design rules and best practices, and it's thinking about how we would actually put this onto a physical device. That's Spartan family, XC, SL, blah blah, and all this stuff. And it's done. Okay. And it's generated lots of output, and some of this is interesting to read. This is how much of that physical device it'll actually end up using if we go ahead and we configure that device. About 1% of the whole device. So 2 lookup tables out of 5700, 2 truth tables out of 5700. And so on. So, but mostly you don't look at this stuff unless something went wrong, and it's meaningful to some people. All right, so our design seems to be good. It compiled. It did a timing analysis. It didn't have any strong complaints. So if we used physical hardware, we could load this into the device. We could build a programming file, upload it, and then play with the hardware. But instead, we're going to simulate this. Okay, we're going to try to generate some timing diagrams. So come up here to the top, and there's a checkbox here for implementation or simulation. Change that to simulation. And now right click on the top of this, your adder demo, and say new source, and we're going to add Vero Log test fixture. Okay, so there's the thing that we're designing, an adder in this case, that's called the unit under test. Okay, UUT sometimes. It's the thing that we're trying to analyze and see if it's working correctly. Typically you do that by taking your unit under test and inserting it into something else, which we call a test bench. And the test bench is the thing that feeds inputs and looks at outputs and helps you figure out if your thing is working correctly or not, your unit under test. So that traffic light, that's a test bench for the Lab 6 circuitry, right? So we're going to create a test bench here using more Vero Log. So Vero Log test fixture, and we'll give it a name. I'll just say adder test. And it will want to know what unit we're going to test, and there's only one module we've created, so that should be selected for you anyway. So we'll go ahead and just next through that, and there's a synopsis of everything we've said, and we'll say finish. And we got new Vero Log code here. Okay, so it's written some Vero Log code for me. I don't have an easy way to make that font bigger. Module adder test. And it's got A and B. These are listed as registers. We'll talk about registers in a bit. It's got an output sum. And it's got this thing here that says add UUT, that's unit under test. Okay. And this is saying basically take this module called add and make a copy of that and connect these things, A, B, sum, to certain points in that, that module that we're testing. We don't really need to understand that. It's writing that for us, okay, and it's writing it in a good way. What we need to do is add some stimulus. So all of this is set up. At this point, we can say, I want to set A equal to this, I want to set B equal to that. And it will do that, and it will see what the output's equal to, and it'll show us in a nice little timing diagram. Okay, so this is also specified in this other document, which is Introduction to Vero Log Programming. It talks about test benches and what some of these things mean. But here's all we got to do. So we can say something like set A equal to 1, semicolon, and then we can say number sign 10. Number sign 10 means wait 10 nanoseconds. That's going to give time for our circuitry to do its thing. So we're asking the simulator to set A equal to 1 and then wait 10 nanoseconds. And then let's set B equal to 1 and wait 10 nanoseconds. So now our output should be 1 plus 1 is 2. And now let's set A equal to 3 and B equal to 2. Don't forget your semicolons. And wait 10 nanoseconds. And I can put some comments on here. some should be 1, some should be 2. If I said A equal to 3 and B equal to 2, some should be 2 plus 3 equals 5. And I can set A and B equal to 3. And there the sum should be equal to 6. All right, you see what we're doing? All right, we're just specifying how to drive the inputs, and it's going to make us a little picture of what the outputs look like in each of these. All right, so ideally we'd probably want to go through all the possible combinations of A and B, but we're just doing some sample testing here. So let's save that. And down here under Design Utilities, interesting. Okay, so click on Adder Test and expand this. Okay, so first thing you're going to do is click Behavioral Check Syntax and double click that, and that'll check the syntax of what we've put in. Oh, wrong one. Oh no, I did it. Ignore that. Okay, double click Behavioral Check Syntax. So behavioral check syntax completed successfully, that's good. Okay, now double click Simulate Behavioral Model. And you get a pop-up window. And I can expand that, and here's my timing diagrams. So I'm just going to control scroll wheel. I can't make it any bigger. So I can click anywhere and move my cursor where I like. But this is showing like 1 picosecond per line mark. This is like heavily zoomed in. So there's a little symbol up here. It's actually a magnifying glass with some arrows pointing in the corner, but that's impossible to know. Click on that thing. There's a picture of it in the write-up. And that zooms you to a useful resolution. And so I can click anywhere that I want, and I will see over here on the left the values of, in this case it's A and B and sum. Let me move sum to the bottom. So A is on top, B is on the middle, and sum is on the bottom. So right now at this point, A and B are both 0, 0, and the sum is also 0, 0. If I click over here, A is 0, 1, B is 0, 0, sum is 0, 0, 1. That's 1 plus 0 equals 1. If I click over here, A is 0, 1, B is 0, 1, sum is 0, 1, 0, 1 plus 1 equals 2. If I click here, it's 3 plus 2, and there's a binary 5, 1, 0, 1. And if I click over here, it's 3 plus 3 is 6. And I can expand these and see the individual values. So at this point, A0 is a 1, A1 is a 0, that's the 0, 1 for A, and so on. But it will also put these together for you and show you all 3 bits if you like. Right? So there's a good timing diagram. And our adder seems to be adding. So the circuits that you're doing for lab 7, right, these circuits, you write the Vero Log code, test it out with the simulator, and try to come up with a test bench that stimulates the inputs in an appropriate way to see if the circuit's working correctly. And if it is, right, then take this timing diagram and copy and paste that into your lab report. And you can highlight things on it, right? You can annotate it with your favorite markup tool and say, you know, here such and such happened, and you can see the output over here is what it's supposed to be, and so on. Right? So this is a tool for testing your circuit, debugging your circuit, and then documenting your circuit. And there's you know, a zillion options for this software, and we're covering a really tiny set, but there's lots of things you can do. Right, you can zoom in like that. You can change the radix, so if you wanted to display things in decimal, you could do that, and so on and so forth. All right, so I know that's a lot, but what questions do you have? It's a lot of steps, but once two things. One, once you get used to doing this, right, it's fairly straightforward. It becomes kind of second nature. I mean, compiling a program in C and running it takes a lot of steps. But once you're comfortable with it, right, it's kind of second nature. GCC-O, blah, 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 right? Same thing with this. But also, once you have a design and you're in the process of compiling it, running the simulation, seeing if it works, going back and making changes, that process gets really, really efficient. Okay, so let's say I was trying to make a subtractor, and this is clearly not subtracting correctly, right? So I can kick out of here. And come back to my adder and say, oh yeah, I wanted a subtractor, so I should have subtracted. Okay, well, I'm just going to save that, and I'm going to come back here. I'm going to rebuild it. And you go grab a quick cup of coffee for the 2 minutes it takes, or the 1 minute it takes. If you have a faster machine, this is really fast. They make nice use of like multi-cores and stuff. Alright, so we're done. Our little spinning circle stopped spinning. So I can go over here to adder test. I can check the syntax. Syntax is fine. I can go ahead and run it. And there's my map, and I can zoom in. Right, and so now I can try this again, and 1 minus 1 is 0, or put this on the bottom. 1 minus 0 is 1. And over here I've got 1 minus 1 is 0. And over here I've got 3 minus 2 is 1, and so on. Right, so it's a pretty rapid debug cycle once you've got all this set up, right? But to get it started takes a little bit of effort. And it's doing, the tools are doing a lot of work for you underneath. So for example, I can come over here, let's go back to adder demo. I can come here under tools, and I can say Schematic Viewer, and I can say show me RTL as register transfer language. It's kind of a block diagram view of your circuit. And this is what it sees my circuit as. It's a block that has two 2-bit inputs A and B and a 3-bit output sum. It's a system diagram of it, right? And if I double click on this, I can start to see a little bit of what's inside. And we don't necessarily know what all this means, but there's some stuff going on. And I think that's as far as I can click in. But here's the fun part. If I do the same thing, but I say Schematic Viewer and I say show me the technology view, check this out. There's our adder. Click through it. This is what the adder looks like. So it's using these 3 lookup tables. A lookup table is just a hardware implementation of a truth table. That's a multiplexer, right? Remember, we can implement any function we want with a multiplexer just by setting the 1s and 0s on the inputs. Well, there's these multiplexers that correspond to something, right, that's ultimately giving us our 3 bits. And we can click on one of these lookup tables, and there's a picture of the schematic. That's the equivalent circuit that it implemented for us. And we can click on the equation tab, and there's the equation that it came up with. So exclamation marks for nots, stars for ands, pluses for ors. And we can ask to see a truth table of it, and there's the truth table values, and it'll even show us a K-map. Right? So it's using all of this stuff that we've been doing in 250 in order to come up with this implementation, right? Which is why it takes so long to run. Because it's doing all this heavy processing, but you know, it's building that circuit for us out of a multiplexer with a bunch of 2 input gates and some inverters. And we can look at this lookup table, and that's a simpler circuit, right? That's the low bit. Well, what is this? Input 0, input 1, those are the 2 low bits going in. Anybody recognize this? Yeah, this is an exclusive OR, right? It's the sum bit from our half adder. It's taking the first bit complemented, ANDed with the second, or the first bit ANDed with the second one complemented. And if either of those are true, the output's 1. That's the least significant bit of our sum. And if we look at the equation, there's the old equation for an XOR, right? Not A or and B, or A and not B. There's the truth table, classic checkerboard pattern, and there's the K-map, classic checkerboard. And lookup table for most significant bit, not too bad. And then if we actually program our chip, we can actually go in, we can look at a picture of the inside of the chip, and it'll show us which blocks are allocated and where all the wires are, and it's this big rat's nest, and it's really fun to look at.
Look at the K-map. There's 2 colors. There's green and red. Which one represents 0 and 1?
I'm going to guess that green is a 1, just because I'm biased by traffic light politics. This should be an XOR, so 0, 0 should give us a 0. So yeah, 0, 0 is red, that's a 0.
So red 0
and green is 1. So 0 plus 1 is 1, 1 plus 0 is 1. 1 plus 1 is 0. Good question, I never looked at that before. All right, so your Lab 7 is all about basically working with this software, right, and getting a little more comfortable with it and doing some Vero Log design. But your first experiment in particular, this document already has the Vero Log code that you want to use, right? So it's really just kind of following the steps and getting this thing to work. And it may not work, okay? You're being warned up front. It may not work the way the document says, because the document is a year old. And this stuff is all moving target. The underlying operating system changes because it's Windows. The software changes because it's a commercial product. But see what happens. And if it's not working, right, grab Izad or me and we can help you. And then we can update the document if needed. But there's lots of places things can go a little sideways. All right, so other questions? All right, so let's talk more Vero Log. So we haven't even gotten to the funnest part of Vero Log. So we know we can do things like make an add circuit, right, by saying, you know, sine sum equals A plus B, and it just adds miraculously. And if A and B are 16-bit numbers, it's the same line of Vero Log that synthesizes this new circuit for us. So let's talk about sequential circuits. So we're almost always going to have a clock when we have sequential circuits. And we kind of need to change our mindset and think about state machines. We're not going to be thinking about state diagrams or big wide tables of present state, next state, but we still want to be kind of in the mindset of state machines, of things that are happening on clock ticks. Okay, so there's always going to be a clock kicking around the system. And so let's think about a counter. Let's make a counter in Vero Log. So we're going to have two inputs, and I know I said before clocks aren't considered inputs, but for Vero Log they are. They're just another signal we feed into our circuit. So we're going to have a reset line which sets the output to 0. We're going to have a clock line which increments the count, and we're going to have an output which shows us the output value. So we have to label inputs and outputs. So reset and clock are inputs. And I'm going to say output is out. I'm going to put something special in here. So I'm going to use the keyword reg, which means register. And so far we've been dealing with wires. So if we say that out is a wire, it's really just a piece of wire. It doesn't have any particular value unless we connect it to something that's producing a value. So if we say assign out equals A and B, we're connecting it to the output of an AND gate. So that's going to give it a value. A register is actually a flip-flop or a set of flip-flops. It's something that even if it's not connected anywhere, it can still hold a value. And our counter is going to bump up its count each time the clock ticks. That means it has to remember its count value between clock ticks. So we want a register here. So we're going to make a register, and let's make this 4-bit counter. So I'm going to say reg bracket 3 colon 0. It's kind of like specifying an array, if you like arrays. So that's our variable out. Okay, so there's one really important keyword for sequential circuits. That's the word always. And the basic idea is we can say always when something happens, I want you to do this. And we can list a bunch of Vero Log code inside. So this is something that we can call event-driven behavior. This is what modern programming is like on a plain old CPU. When you write code in Java or Python, more often than not, you're writing event-driven programming. When you write an Android app, it's event-driven. You basically specify code that says when your GPS position changes by more than 2 feet, I want you to run this code. When somebody touches the screen, I want you to run that code. When this timer that I'm setting up has expired after 15 milliseconds, I want you to run this code. Right? Event-based programming is what we mostly do in software. It's what we do in Vero Log. So we write these always blocks. And so a typical always block would be always @ sign. And then we can say something like positive edge or negative edge of the clock. So if I say always at pos edge clock. And this means any time that the clock ticks from a 0 to a 1 at that edge, I want to do the following. So we say begin. And everything from there to end gets fired whenever the clock ticks. Okay, so I can put in if statements. I can say if reset. So if reset is equal to 1, what do I want to do? I want to set my output equal to 0. All right, When we have registers, we use a special form of assignment. We actually use a less than followed by an equal. So it's like an arrow pointing to the left. And you don't want to say just out equals 0. It'll compile, it'll even work sometimes, but it's really not right. So if reset is true, then we want to set the output equal to 0. Else, we want to assign the output to be output plus 1. And again, not out equals out plus 1. And that's really our whole module. So what's the behavior here? This is going to build a circuit which does the following. Whenever the positive edge of the clock occurs, it's going to change the value of this output register, these four flip-flops. And what is it going to do then? It's either going to set them all to 0 if the reset line is high at that point, or it's going to set it to the current value of that register plus 1. And so that's going to make a counter.
What does the less than sign in front of that?
Less than equal is an assignment statement, so it's... Think of it as a single symbol. It's like an arrow.
Yeah, I know, but like you said, not out, so I thought that meant something different in the context of Vero Log.
So the less than equal says I want to assign this value to that register, right? Don't write out equals 0, right? Maybe I should not use the word not, because that's a logical thing.
Oh, okay.
Don't say out equals 0. Yeah. I'll tell you more truthfully what that means in a few minutes. So this is a positive edge triggered 4-bit counter with a synchronous reset. Synchronous means I can raise reset anytime I want, but it doesn't do anything until the clock ticks. So I can raise reset and drop it, and if the clock hasn't ticked, no reset happens. But if reset is true when the clock ticks, counter will get reset to 0. So let's see if we can write this. I'm not going to change the name add because I need to change something over here. Well, let's just start a new project. Let's not be goofy. Let's do file, new project. We'll call it a counter. We'll click through, and most of these things are going to be able to take defaults now. So new source, Vero Log source. Vero Log module. I'll just call it main. It's going to have an input reset. It's going to have an input clock, and it's going to have an output. What do we call it? Out. So that's an output, and it's a bus, and it's 3 to 0. All right, so I'm going to put my register statement down here to say output is a register, and it's got 4 bits. So always a positive edge clock begin. If reset out is assigned to 0, else out is assigned to out plus 1. There's the end, and there's the end of the module. And when you save this, I'm using Control S to save because I don't like point and click. When you save this, it will check your syntax for you at the same time. And so I'm getting some red X's over here. Look at the first one, okay, and it says line 30, syntax error near else. you can click on this and it points right here. There's a syntax error somewhere right here at the beginning of else. Well, the problem is actually right up here. I didn't have a semicolon. So it thinks I'm saying out is assigned to 0 else, right, which it doesn't like. So it should get you pretty close to where your error is, right? And then I'm just going to save that, which will check the syntax, and it says completed successfully. So now we're good to go with that. Let's go ahead and do the synthesis. Actually, I'm not sure you have to do this just to simulate. But it's fun to do anyway. It's your coffee break. Alright, so we're done with that. Let's go back up here. Let's switch to simulation. Let's say new source and make a Vero Log test fixture. We'll call it tester. It's associated with main, which was the module we just defined. And so now we're going to write some code down here, add stimulus here. Okay, so something else we can do, and this is on page 7 of the Introduction to Vero Log Programming. We can put another statement inside this test fixture, and this goes before the initial begin. So I can say always begin, and this is something that's always going to happen. And what I'm going to say is wait 5 seconds, and then set clock equal to not clock. So wait 5 seconds and then basically toggle the clock. This is how I'm going to generate a clock that constantly goes between 0 and 1. So always begin, wait 5 seconds, and then set clock equal to not clock. And that's the end of our always block. Alright, so we add some stimulus here. So let's do the following. Let's set reset equal to 0. I have to initialize the clock. Yeah, let's set the clock equal to 0. Let's wait 10 nanoseconds. Sorry, let's set reset equal to 1. Let's wait 20 nanoseconds. Let's set the reset equal to 0. And then let's wait, I don't know, 200 nanoseconds. So what are we doing? We're turning the reset line on high, waiting 20 nanoseconds, which is about 4 clock ticks, so that should be plenty of time to reset. Then we pull the reset line down low, and we're just going to wait for 200 nanoseconds, which is 40 clock ticks. Should get through lots of different count values. So let's come in here to the test module. Let's check the syntax. And it says it failed, so let's click on the first error. Does not like the word end here because I forgot my semicolon. So we'll save that, redo the check syntax. That completed successfully. Let's simulate it.
I think that's the most common error that
Semicolons always, absolutely. So let's zoom out. And you can see that for the first 100 nanoseconds, this top line, which is labeled output, is red. It's got 4 x's, and it means it's an undefined value, right? The value is xxxx. But when we come over here, after the reset line went high and then low, right, our output value was 4 zeros, and you can see it inside the little shapes up there on the top. The output was 0, 0, 0, 0, and then 0, 0, 0, 1, and then 2 and 3, and so on. And it's counting in binary, right? And I can scroll over, and it goes all the way up to 1, 1, 1, 1, and then it goes back to 4 zeros. That's our up counter. I can expand the output, and now you can see the actual individual traces for each of the 4 bits. And the least significant bit, which is down here right above the clock and reset, toggles every other clock tick. The next bit toggles half as often, the third bit half as often, and the most significant bit half as often as that. So here's the value 9, and so on and so forth. So there's your counter. Okay, so everything we've just done is like more than sufficient to get through Lab 7, I believe. Right, because we've done sequential behavior, but it's like C, right? There's a handful of statements that make up the C language, and you can do just about anything with C. You've got to know how to take that handful of statements and put them together, right? So the initial challenge is learning the building blocks, right? The always, where do you put the semicolons, clock equals tilde clock, and so on. But then the bigger challenge, which is also the fun part, I think, is actually figuring out how to put these things together. And you have a simulator that will help you in that exploration, right? So you can use Lab 7 as a guide, but you can also try things yourself, right? Just like teaching yourself programming. You know, how would I do such and such? Well, write some code and try it. And this timing diagram generation is like a really great debugging tool. It'll help you see exactly what's going on inside. It may not tell you why that's what's happening, right? But if I expected, you know, so if I was doing my traffic light circuit, for example, I could use this and I could say, well, priority should have been 1 here, but it was actually a 0, and why is that? And I could go back and say, oh, because my delay circuit delayed for 4 clock ticks instead of 2 or something, right? It's really an X-ray of like everything that's going on inside your circuit. So definitely, you know, do experiment 1 first on the lab, which means going through the first 2 sections of this and getting down the mechanics of how do I run the software and so on. And like I say, this afternoon I'm going to try installing it on the Collaboratorium machines and make sure that's doable, and I'll let you know what comes of that. In worst case, you can just install it every time you want to use it. But then definitely read through the Vero Log programming. This document talks about something called the Icarus software, and don't get bogged down in that because we're not using the Icarus software because that got broken somehow on the machines. It doesn't run. But the Vero Log part of this, right, is still totally useful and valid. So look through that. And then ask lots of questions. You can post discussion questions on Canvas, and almost guaranteed any time that you have a question, other people are going to have the same question, right? And it's going to be really efficient if you can post your questions on Canvas under the discussion area, and either other people can chime in, or if nobody responds after an hour or 2, I'll try to chime in and point you in the right direction. But this way, everybody who has that problem can sort of see the results and build on further questions and so on. So that's a good resource to get in the habit of using. All right, so let me just eyeball the homework for you. All right, so Vero Log homework, and this is good sample code also, right? So best recommendation I have for learning Vero Log: get some sample code, right? There's lots of sample code in here. There's sample code in the homeworks. Type it in, see what it does, make some changes. Okay, I'm convinced after decades of programming, this is probably the best way to learn how to program. It's just by writing code. Even if you don't know what it's going to do, type it in and find out. Right? Don't do this for system level code while you're like root, but write some Vero Log and see what it does, and then make changes to it. Right? So here's something which is supposed to do this particular logic function. Can I change it to do A bar BC or ABC bar? Right? Well, all I should have to do is put a tilde in front of the C down here, right? But do that anyway and start making more changes. So sample code's available. Okay, so question 1, implement this logic function. It's going to look a lot like the solved solution. Question 2, positive edge triggered T-latch. Really, really good exercise. He means flip-flop, so T flip-flop in Vero Log. So what do? Well, when the clock ticks, so always at pos edge clock, if T equals 1, out equals complement of out. Right? That's the behavior you're after. There's no inverted, you can build it with NOR gates connected to each other, cross-coupled, and so on and so forth, but describe the behavior. When the clock ticks, if T is equal to 1, I want to toggle the output. Well, that's really one line of Vero Log. Well, it's an always statement, and then it's one line of Vero Log. So behavioral explanation. And here's a JK flip-flop, right? So always at positive edge of the clock, and here's a fancy expression that sets Q to the right value based on J and K. Implement a 4-bit binary up counter. Well, we just did that. Make a 4-bit binary down counter. Question 5, 3 to 8 decoder. So 3 bits coming in, choose one of 8 outputs, right? Question 6, go the other direction, 8 lines coming in, choose one of those to send to the output based on a 3-bit value. So this is the mux-demux pair. And then you gotta love question 7, traffic light controller for a 3-way intersection. It's a whole lot easier in Vero Log once you understand Vero Log. No wires involved. And so I posted a note when I put the homework on Canvas saying you can assume you have a clock coming in at a frequency of 2 seconds, or a period of 2 seconds. So assume there's a signal available, you can call a clock that ticks every 2 seconds, and you can use that in your design. In practice, you usually have a clock that's like 50 megahertz, right? So how do you get a 2-second tick out of a 50 megahertz tick?
Are you supposed to like submit it online, like we make a file for it, or?
For the homework?
Yeah, like
on paper. So you probably want to computer generate it. But you're going to be writing the code and testing it in the simulator, right? Presumably, unless you really trust your Vero Log. So yeah, just turn it in as a hard copy.
And then put down the timing diagram for it?
If you do a simulation, take a snapshot of the timing diagram, put that in. I just copy and paste it. Does that make sense?
Yeah, it depends on how much ink I need to use to put it out.
You can reverse video it, right? Find your favorite video. Actually, I think in the simulation you can change the background to white and such, but if not, just throw it into ENGR or some other graphics program and just flip the video. Just do a negative. All right, so 3-way intersection, right? Every time the clock ticks, check your sensors. If there's a car that has high priority and the light's not red, go into a new state where you change some other color to yellow, right? So set a flag variable somewhere, a state variable, and set your outputs according to the sensors and the state variables.
For my view, would you set there to be strictly 3 inputs and 8 outputs?
So there's 3 select bits. So what does a decoder do? 3-bit binary to 8-line decoder. So you're going to have 8 outputs and 1 input. And you're basically routing that input to one of 8 outputs based on 3 select lines. So something like this. Right, 8 inputs, 3 selects, and an output.
Okay, so these selects don't actually count as inputs, do they?
They'll be inputs to your Vero Log module, but no, they're not the 8 inputs. Well, they don't use the word input in here. So it depends what you mean by inputs. But yeah, your system diagram, you would have a total of 11 inputs. Right, but these 3 inputs are being used to select one of these 8 inputs to send to the output.
Right.
So it's like a demux.
Yeah.
And then 8 is an arithmetic logic unit, so a block which can add, subtract, and multiply 8-bit numbers. So here's your ALU. Here's number A, 8 bits going in. Here's number B, 8 bits going in. Add, subtract, or multiply, that's 3 different functions. How many bits do you need to specify one of 3 things? You can do it with 3. You only need 2, right? 2 bits, you can specify 4 things. So you can have a function, which is 2 bits. If you're going to be nice to your user and you want to let them multiply any 2 8-bit numbers, you should probably have a 16-bit output. Right? If you add 2 8-bit numbers, you only need 9 bits. And so here's your output. And it's up to you what 2 function bits should specify add or subtract or multiply, and what should you do with that 4th combination. It's your choice, it's your circuit. Design it how you like, right? And then write the Vero Log. The Vero Log is minimal, right? It's all the setup of this is an 8-bit register, that kind of thing. It takes most of the work. But to add, subtract, or multiply in Vero Log is just plus, minus, or star. All right. Get going on that. I will post and let you know what happened with trying to get Vero Log going in the lab. Send me questions or post discussion questions, and I will see you next week.
What is it? What do you mean by active high and active low on SIP 5 Unit 6U?
Oh yeah, active high means that whichever one is selected, the input gets copied and the others are outputting a 0.
Okay.
Active low means that everything outputs a 1 except the one that's selected and that outputs is...
Oh, so that output, okay.
Yeah.